So I decided that I'm going to do an SI session on this because I think it fits the best, would be the most exciting format, and um, it's something I'm really familiar with as an SI leader. So, kind of what I decided on, as you can tell by my whole intro SI slide. But let's talk about Archimedes and his inventions and how he kind of changed warfare and science. So, most people recognize Archimedes for his eureka moment in the bathtub. So, basically, this eureka moment was he was sitting down in the bathtub and he realized that the water level was rising as he sat down more in it. Now, this was significant because he ended up using this, well, initially to figure out whether a gold crown was actual gold or fake gold. But the more important overarching discovery with this was Archimedes' Principle. So, what Archimedes' Principle was basically it stated that the amount of a fluid displaced created that amount of force upwards, so that mass amount of force upwards. So if you have a less dense object than water and you put it in water, it's going to float because it has less mass, right? So let's draw this out. So we have this. This is going to be a water line. We have a less dense object. So we have two forces going on here. We have our weight force and a buoyancy force. So this buoyancy force is Archimedes' Principle. What this buoyancy force is, like in a pictorial representation, is it's this weight of water. So that volume of water is equal, the mass of that volume of water is equal to the total mass of that object if it is floating there. So that was a very significant discovery, and it leads into kind of one of his machines. But I'm going to talk a little bit more about this just to make sure you guys have a good understanding of it, because it is a very important principle. And if you've taken like general mechanics here or probably anywhere, you'll learn this principle. It's it's very important for a reason. So let's say, I'm sure you guys can guess at this point, if we have this heavier object and we drop it in, it's going to sink at the bottom because that buoyancy force is not enough. However, it will sink slower. So we have a force equation, F equals ma equals mg minus, actually, we'll do it the opposite way. We'll say, that way it's a little bit more standardized. We'll say b minus mg. B is our buoyancy force. So as this is floating down, it has a constant buoyancy force of b pushing it up and a larger mg force. Mg force is our weight force of the object. So this is for an object more dense than water, and you can basically, whenever you solve all this out, you'll find that the acceleration will be lower than that of an air, which you can expect. When things go down in water, they go down more slowly than they would in air. So that makes sense. So hopefully you guys kind of have an idea of how this principle works. It's, like I was saying, significant for an ridiculous amount of reasons, but we are going to connect it to the Claw of Archimedes. So in Plutarch's The Life of Marcellus, he kind of talks about this machine. I left a quote down here that I'll just read real quick. So at the same time, huge beams were run out from the walls so as to project over the Roman ships. Some of them were then sunk by great weights dropped from above, while others were seized at the bows by iron claws or by beaks like those of cranes. hauled into the air by means of counterweights until they stood upright upon their sterns, and then allowed them to plunge to the bottom, or else they were spun around by means of windlasses situated inside the city, dashed against the steep cliffs and rocks which jutted out under the walls, with great loss of life to the crews. Often there would be seen the terrifying spectacle of a ship being lifted clean out of the water into the air and whirled about as it hung there, until every man had been shaken out of the hull and thrown in different directions, after which it would be dashed down empty upon the walls. So this is talking about more than just the claw, but the claw is the big part here in the quote. So I have a couple depictions of the claw. So this is kind of like what a lot of people think of. This one on the left. This is like your whole famous depiction. There's a claw literally grabbing it and capsizing it. Is that what happened? Well, no. You can't. Creating a claw like that would be impractical. So it wouldn't make much sense, nor would something like that be really feasible if you look at the design, because it couldn't bend in the right ways. But rather, if we look to this picture on the right, we can see kind of a depiction of how it more likely was. It was probably something like this, where you got like it hooked onto the bottom of the ship or some part of the ship and it pulled it upwards. So I was talking about that whole buoyancy section with Archimedes Principle, because if he were to like drop this, you can see how that the sudden buoyancy force would create some like damage and such, which I think is noticeable, because just to kind of further explain that point, the reason it would create damage is because if something heavy is quickly dropped into it, that buoyancy force is going to be more like an impact than anything. Think about if you're belly flopping into water from a great height or something. Like that can be deadly, right? Sorry, my face was in the way. So if we have this big ship, I'm just going to draw it like this, just being dropped into the water, there's going to be a very fast and increasing buoyancy force. Because like I said, the buoyancy force is created by the water displaced, because that water is rapidly going to be displaced as it hits. It's going to act more like just solid ground or something. I mean, obviously not quite like solid ground, but it's going to be a very hard impact. It's also described kind of like they shook around the ships and stuff, knocking people off. It all depends on how they actually designed it. I don't think not that I could find any like actual historical depictions from that time period about how it looked. Probably because I couldn't find anything. But the best thing I could find was this depiction, which I already pointed out, the one on the right. And a very important part of this depiction is our pulley system. So our pulley system right here, and just to kind of get an idea for how pulleys work, I think this picture under that describes it perfectly. So if we have one pulley, it's as if you're basically just pulling it, right? Same amount of weight, whatever. If we have this double pulley system, we can use half of the force to lift that same weight. Okay? And same, if we go to triple pulleys, we can use a third of the force. 4 pulleys, we can use a fourth of the force. So what pulleys allow us to do is lift very heavy weights with less force. Now the only downside to pulleys is that there is less force, but it takes more like distance. Like you have to pull it farther for it to actually work. But it's still a very effective system for obvious reasons. You wouldn't be able to lift a boat out of the water without a pulley system. It's just not gonna happen. It's not feasible by any means, especially with this time period. So you can see there's this little pulley system that I already pointed out. Now this depiction shows it with a double pulley. If I were to guess, it would probably be more than a double pulley because Archimedes, while pulleys already existed before Archimedes, he improved upon the design of them. So, basically, like, we don't have an actual historical depiction, which is unfortunate, and I wish we did. But more than likely, I would guess it's a few more pulleys just to lessen that force needed. This also shows like a cattle pulling it. It could have been a lot of things because Archimedes also understood how levers work really well, which I will talk about a little bit. I'm gonna scroll down. So basically, levers utilize something called torque. So I'm gonna just picture a wheel, because if he happened to not use like the bowl or something, then a wheel would be pretty practical, where you have just a giant wheel with people pushing on each part of it. Right. So basically what this is called torque. That's the Greek letter tau. I'm terrible at drawing it, but I'm attempting. And what torque is equal to is it's R cross F, where R is our lever arm and F is the force. So I already drew our forces here. And our lever arm is going, I'll do this in a different color, is going to be R, this. So the difficulty with cross products is it's hard to visualize. The torque force isn't going to the left, to the right, up, or down. It's actually going to be coming, if it's rotating counterclockwise, out of the page, if it's rotating clockwise, into the page. But that doesn't matter too much. You know that torque is basically, in this context, would be used to ravel a rope. So it'll ravel a rope in some way around some beam. That's really what matters here. So we have R cross F. This allows us to get extra leverage. So just as a common analogy, think about your door. If you push your door from that outside edge like you're supposed to, it's super easy to open and close. Now go to your door and push it closer to the hinges. You won't be able to move it at all. Or, okay, you will be able to move it, but it'll take more effort. Sorry. It won't be able to move it at all was the next part. So something about cross products is if something is parallel, a cross product is equal to 0. So let's say you push on something like that, like I drew in the purple force, it won't create a torque force, obviously. If you go push on your door, like push towards the hinges on the outside, it's not going to go anywhere for obvious reasons. So that's just a basic rundown on torque. So I don't think, like I was saying, I don't think there's any like actual explanation of exactly how he did it. I looked pretty hard for it, but that would be my guess. If it could have been a bowl, but I feel like that would be unreliable. So I would assume it would be some kind of wheel. You'd have some well-made pulley system. That way he's utilizing two types of leverages, torque and pulleys, just to like make it as easy as possible to hoist these ships up. Right. And then as for shaking it around, that's kind of similar concept, like that you could design a system so that it swivels at the top, so that it can shake it around and knock a bunch of people off, or it can just slam into the ground, just kind of whatever. Even like if you were to do the wheel system, a good way to make it just slam is if he installed some kind of like a releasable kind of like free spinning object that the rope was wrapping around. But I would go ahead and say that's probably not the case. But I don't know. Like I said, can't find an actual depiction. These are just kind of my guesses as to exactly how it works. But the Cloud of Archimedes was really famous. it probably did exist from what I was finding. Most scholars think some form of it existed. So yeah. But this quote mentions like he was hurling huge beams from the walls and like great weights were dropped from above and stuff. So you could also use this system to drop like big rocks and stuff and crush ships that are close. But obviously that's not as effective as something like a catapult. So Archimedes actually kind of revolutionized the way catapults were made because he applied mathematics to it. Because prior to him, catapults were in use and such, but they weren't in use effectively because they didn't apply any math. They just kind of like were like, oh, we could do this and launch stone. Ooh, caveman. No, not caveman, but they weren't made in like an intelligent fashion that really utilized mathematics to maximize its like potential. So I have another quote I'm just gonna read through. Sorry if me reading through these quotes is kind of annoying. I know I don't have the best reading voice, but I don't know. If you don't want to listen to me, skip ahead a little bit and read it yourself. So, this was the siege equipment with which the Romans planned to assault the city's towers, but Archimedes had constructed artillery which could cover a whole variety of ranges, so that while the attacking ships were still at a distance, he scored so many hits with his catapults and stone throwers that he was able to cause them severe damage and harass their approach. Then as the distance decreased and these weapons began to carry over the enemy's heads, he resorted to smaller and smaller machines and so demoralized the Romans that their advance was brought to a standstill. In the end, Marcellus was reduced in despair to bringing up his ships secretly under cover of darkness. But when they had almost reached the shore and were therefore too close to be struck by the catapults, Archimedes had devised yet another weapon to repel the marines who were fighting from the decks. He had the walls pierced with large numbers of loopholes at the height of a man, which were about a palm's breadth wide. At the outer surface of the walls, behind each of these, and inside the walls, were stationed archers with rows and rows of so-called scorpions, a small catapult with discharged iron darts, and by shooting these embrasures, they put many of the marines out of action. Through these tactics, he not only foiled all the enemy's attacks, but those made at long range and any attempt at hand-to-hand fighting, but also caused them heavy losses. This is from Polybius Book 8, another historical figure. So, I have two pictures on this. We have the catapult, and we have what's called a belly bow. So the Romans basically saw Archimedes' design of catapults and this belly bow. I don't think he called it the belly bow, but the Romans called it the belly bow when they stole the design. So they actually took one of these back to Rome and they were like, we have to be able to replicate this because it was such an effective machine. So what this belly bow does basically is this large thing. You can put it like up on your belly. You can look up a video of it actually. It's kind of neat. And you put this iron dart, as it describes, in it. So like an iron kind of rod thing. And then you can pull it back and launch it. So it's going to be something much stronger than an arrow and more effective for that reason. At least for certain things when you're using it as artillery. And it's also been described in a few things. I don't have a quote here because I didn't want to overwhelm it with quotes, but his catapults could launch like very heavy objects compared to what other catapults at the time could launch. And I'm just gonna kind of talk about the physics behind this because this is a physics-based project. I'm sure you could have told. I don't think I exactly explained that, but I think everything is pointed towards that. So, both of these work off of energy, basically. So, we'll do this in green because I like green. So, I'm not sure if you know what the energy equations are, but I'll tell you that they are delta K plus delta U. So delta K is our kinetic energy, and U is our potential energy. If you don't know what delta means, it just means the change in. So it's nothing like crazy out of this world. This is mostly basic mathematics. So there is a principle called the conservation of energy. We're going to be kind of using that to explain the rest of this, just because for the most part it's going to hold true. Obviously, nothing is truly conserved. There's going to be friction and such, and certain forces that are releasing some of the energy as heat, but we're just going to ignore that. So when energy is conserved, energy total is going to equal 0, basically. So that allows us to say that 0 equals delta A plus delta U. So we're going to go ahead and expand this. So for K, we have 1/2 mv squared. I'm just going to do it this way to save some time with brackets. This just means that you're going to have the final velocity minus the initial. And then the other one is, most people know mgh for our potential energy, but we have another one that's very important on this one, which is our spring's potential energy, which is going to be 1/2 kx squared. Oh, you guys can't see that last part. So I'm going to just kind of explain what all these variables mean. M is the mass, V is the velocity, G is our gravitational constant, H is our height, K is our spring constant, because as you can see, these effectively work off of springs. And then X is our distance from the spring's equilibrium. So just to kind of explain what exactly that means in relation to this, we have an equilibrium for this bow here. And if you are to pull this back, we'll say here to this tick, this is going to be your X. Cool. There is another form of kinetic energy, I suppose, might be worth mentioning, but we're not really going to talk about it. It's this one, but we're not going to worry about it, just as to not overcomplicate this too much. Okay. So we have, this is our X. So we'll say that, oh, that's in white. I'll do purple. Our equilibrium point for our catapult is going to be this straight up purple line. So this amount is going to be kind of our X. It's like, if you're actually mathematically working out, it's going to be a little bit different, but we're just going to call it that just because it kind of makes it the easiest. There is some like cogwheels down here that's doing a lot of the work, and the gears, I guess. The gears have to be like a very specifically made, and like to cause it to launch as well as it did, which is why mathematics was so important, Because before they were just kind of like, putting these things together, it works, whatever. And then Archimedes was like, well, if you add some mathematics, it can be a lot more efficient and work better. So, also worth noting that depending on what you're looking to get, a better design would allow you to kind of change the angle of this stopper. So like maybe you could make the angle here. It would make it a little bit easier to change your distances, but that's kind of besides the point. Let's go back to energy right now. So we have MGH. Well, that will take effect. We are going to kind of ignore it for these purposes, because what we're actually looking at is okay. So these are going to be for the belly bow. These two that I crossed out would be for, or not these two. These two would be for our catapult. Belly bow. So we'll just do this. 1/2 mv squared plus 1/2 kx squared fi fi. I'm only doing the bracket thing because I'm lazy, and I could write the rest out, but I don't think you guys actually want to work through all the math with it. So basically, our initial for our kinetic energy when this is pulled back is going to be 0, because it is stationary, right? So I'll just do a quick little drawing. We have this bow, and we are pulling it back with our bolt. It is not moving, right? So because it's not moving, I just threw my stylus, our velocity is 0. So our initial kinetic energy is just going to be 0. And our initial potential energy is going to be the maximum it will be. So it depends on how far you pull it back. It'll be at that maximum. And then whenever we release it, so we release the bow, you guys should be able to see this. And we have our little dart flying. So you can see our x is back at equilibrium. So our final potential energy is going to be 0, and all of that potential energy has been converted to kinetic energy. So this allows us to calculate the velocity of our bolt, basically. With some caveats, but like I said, we're going to pretend energy is entirely conserved because that makes things easier. So basically, as you can see with the spring system, because x is squared, it creates a much larger force than certain other systems. And bows in general are spring systems. This is a type of spring. This little bow thing, it springs it upwards. You could also do like another type of spring, the more commonly known spring, obviously, but whatever, works. But in this case, they used kind of a bow design because that's what they knew, and that's what was functional and easy to manufacture at the time. And just to talk a little bit about this. Oh wait, I had one more thing to add on that last part. I'm going to move this over here. So you can figure out the bows. I'm just going to do this quickly because it doesn't matter much, and I don't think they did a bunch of mathematics on this to figure out how to fire them. But you can use kinematics to figure out how This is a kinematics equation. It's your most basic one. I'm just gonna go ahead and write down the rest really quickly, actually. We're just gonna write down those two. Those are the important ones. So you can use these to figure out kind of exactly where it's gonna land and the projectile or the arc of the projectile and everything. So a super quick explanation is we are going to use the V we calculated and use that for our V naught. Because what that V was the instant that bolt was released. It had that velocity. Or not the instant it was released, the instant it left the system of energy, I guess. It's going to be leaving with whatever velocity that is. So we can plug that into this system. If we are looking for a horizontal component, we're going to just ignore air resistance because it's so negligibly small. So this is going to go to 0. And you can find out how far horizontally it traveled, depending on time and arc. And you can find time by doing this same thing, except in the y direction, with v naught t plus, no, actually, in this case, minus 1/2 g t squared. Remember, g is our gravitational acceleration. So, whatever arc you fire at, projectiles move. Here, I'll just draw it like this. Move in a parabola. Well, an upside down parabola, obviously. So this, with our t squared, clearly models a parabola. If you shoot it, let's say, horizontally, so there's no angle going to it, your v naught's going to be 0. If you shoot it at an angle, so we'll just say 45-degree angle, with v naught velocity, you can go ahead and calculate our y component of v naught and our x component of v naught. And the x component of v naught is what will go here, and the y component will go here. This is just through some simple trig I'm not going to exactly go over, because I will go over it. Sine of theta equals v naught y over v naught. I'm sorry, I just enjoy physics, so bear with me. And then cosine theta, theta is our 45 degrees, equals v naught x over v naught. If you know SOHCAHTOA, you can do that. If you don't know what SOHCAHTOA is, don't worry about it. That's just how you calculate these components, basically. And then you can go ahead, find out how much time it's going to be traveling, and then you can find out what kind of distance it's going to travel, blah, blah, blah. You can do all that. Don't think they did all that, but maybe they did. The soldiers probably just kind of eyeballed it, or maybe Archimedes told them and mathematically worked it out. I'm not entirely sure. Archimedes, worth noting, was ahead of his time on mathematics. He was using calculus before calculus was even invented, which is crazy because calculus is complicated, and there's certain elements in this stemming from calculus. Like anytime you see a change in like this, the delta, that's coming from a calculus, like the thing per time. You recognize a derivative. There's also the position function is actually equal, or the velocity function is actually equal to the rate of the position function, as you might have been able to guess. This is all pretty cool stuff. So that all relates. And then Catapult's a really similar concept. It works off of torsion. Like I was explaining, it's going to use the energy from that torsion system it has going on down there to launch it. You'll go through a very similar mathematical process. And the reason I was saying that you would want to be able to vary this angle is because if you're trying to launch something the farthest possible, 45-degree angle is the best. If you want to hit something that's closer, obviously you want to change the angle, blah, blah, blah. I'm sure they had some kind of system for this, but that's just kind of me. Also worth noting, you can see a pad on this catapult. This, and there should be one here too. Yeah, you can see one. This is because the catapult, because they still weren't like impressive by how later catapults and trebuchets and such were made, but the catapult would literally just slam into that support beam. So you had to have a really thick support beam and some padding to keep it from shattering. So that's all that is. It's nothing crazy spectacular. And you can see they're using levers and pulleys and stuff to wind this down. Cool. I think I'm done on this part. And that was actually it. He did have another notable thing, his death ray, where he had a bunch of people with mirrors and they would shine lights, like a ton of mirrors, and they'd all try to shine on like a boat mast to light it on fire and ignite it. There's a whole lot of debate on whether A, that actually happened, and B, whether that actually worked, because in stories it sounds like it worked, but there's theory that, or there is an ongoing theory that more than likely something was launched, like an incendiary was launched onto the boats, and he was trying to utilize these still, so it seemed like they were causing the ignitions, but they weren't really. But it's an interesting idea. It was not gonna work out well. And I think those are the main points for Archimedes, like machines and stuff. He was a brilliant man, truly was. He did a absolute ton for mathematics. If you take physics, even now, oh, I just clicked out of this, I'm sorry. Okay, yep. If you take physics even now, you'll still learn Archimedes' Principle. It's an important principle that is applied every day. And he utilized so many different principles just to create these complex machines and hold off the Romans. And it was incredibly impressive that he held them off in the Battle of Syracuse for as long as he did. Without him and his machines, it wouldn't have lasted like nearly as long. Like they probably wouldn't have even lasted a month, but the battle went on for quite a long time due to these crazy inventions he made, and the kind of fear it struck in the Romans because they weren't prepared to take on these kinds of things. So I'm hoping I hit all the points for this, otherwise I'm going to have to re-record this. But as I would do in another SI session, or in any other SI session, that is my actual Insta. If you want to see some cool yo-yoing, I might not plug that as much, but there's my times. That doesn't really matter, but I'm doing this as a mock SI session because I thought that would be the best. So I figured I'd end it here just to, like I usually do, to show the times and such. I'm a little bit unfortunate that I couldn't get the active participation like I do in an actual SI session, but that's okay. It was interesting talking about the physics behind it nonetheless. So, hope you guys have a good one.